Infrared absorption for typical covalent compounds tends to range between 600 and 4,000 inverse centimeters. In that region, there are kind of four distinctive areas in which you can find interesting functional groups that can help you identify compounds. In the between 2,600 and 3,500, you tend to find the XH stretches, X being a heteroatom, so the nitrogen hydrogen stretching mode, oxygen hydrogen, and also carbon hydrogen stretching modes appear in this area. Triple bonds tend to appear, carbon-carbon triple bond, or for example carbon-nitrogen triple bond, a nitrile group, appears in the 2,500-2,000 inverse centimeters. Double bonds, carbon-carbon, carbonyl group, carbon-oxygen, or an imine group, imino group, carbon double bond nitrogen, appear in the region between 2,000 and 1,500 inverse centimeters. Finally, in the lower, in the 1,400 to 600 is what we call the fingerprint region, and single bonds appear in this area, and it's quite commonly very difficult to interpret unless you have access to a database. So what does it mean for when we go to interpret a spectrum? Well, the thing to consider is to focus in the area between 1,400 and 4,000 to interpret bands. That is where interesting bands that are going to tell you information about the structure of your compound are likely to appear. The region below 1,400 is difficult to interpret because you get all the carbon single bonds and carbon hydrogen bonds will appear there, and your molecule is going to be packed with those bonds, so it's going to be very difficult to interpret. The fingerprint region is unique to the structure of the compound. It's not that it's not useful, it's unique to the structure of that particular compound. So if your infrared spectrometry is connected to a database, then you can find a percentage match between your spectrum and spectra that you can find in the database. But for you as a skilled scientist to interpret an infrared spectrum, staying in this region of the spectrum is the most informative part, and the one that is going to give you more information about what compound you are looking at is. That is also useful if, for example, you're looking at an infrared spectrum of a new compound that does not exist in any database. Then you will need to look at this region to try to work out what sort of functional groups your unknown compound has. Alkanes have very unexciting infrared spectra. They don't have any functional groups, only carbon-carbon single bonds and carbon-hydrogen bonds. They are they tend to have very few bonds. Having said that, loads of organic molecules are going to have, organic molecules are going to have carbon-carbon single bonds and carbon-hydrogen bonds throughout its structure, most likely. So they are very common functional groups. There are very common functional groups to identify. You have in this area around 3,000 the carbon-hydrogen stretch, and sometimes if there's nothing else happening in that area, you might also be able to see the carbon-hydrogen bending modes. But the most common ones, the ones that are easier to spot, are the ones in the 3,000 region, the stretchy modes for the carbon-hydrogen bonds. Alkenes have at least one carbon-carbon double bond, and that tends to appear in around 16-14 inverse centimeters. So it's worth keeping an eye for that. They're also going to have carbon-hydrogen bonds, and they are going to be of two types. You're going to have the carbon-hydrogen bonds that are related to the sp3 carbons, the carbon single bonds, because unless you have a very small, for example, if I'm going to draw here This would be the structure of one hexene, so 6 carbons, and with a double bond between 2 carbons. So in the infrared spectrum of hexene, one hexene, you can observe the carbon hydrogen stretch modes are related to the hydrogen, to the 2 hydrogens that are here attached to the double bonds. But you're also going to observe loss of carbon-hydrogen stretching bonds, which are due to all the other hydrogens that are in the rest of the molecule, all the other carbons that are sp3 carbons. And as I mentioned before, the 1640, give or take, inverse centimeters, which corresponds to the carbon-carbon double bond, to the stretching mode of those sp2 carbons. This is the infrared spectrum of one octane, which is an alkyne. In an alkyne, you introduce a carbon-carbon triple bond, and those tend to appear, that stretching mode of the carbon-carbon triple bond, those sp carbons, appear around 2100. It has to be a medium to weak band because that carbon-carbon triple bond is not a very polar bond. So you might observe it, but it can be quite small. You will observe also the carbon-hydrogen stretching bond of the hydrogen that is next to the sp carbon, to a carbon involved in the triple bond. And as you can see, they tend to be quite strong bands. And additionally, you will also be able to see carbon-hydrogen bonds related to the carbon-hydrogen stretch vibrations related to the hydrogens attached to carbons, sp3 carbons. So all the carbons that are not part of the triple bond that again give you quite strong bands. This is an interesting comparison between 2 infrared spectra, both corresponding to octane, 2 isomers of octane. In the top, the triple bond is in a terminal carbon, and the spectrum in the bottom, the triple bond is in the middle of the molecule, in carbon 4. And as you can see, you can observe the alkane carbon-hydrogen stretches in both, because you have plenty of carbon-hydrogens, sp3 carbons, hydrogen bonds, therefore that they appear in the structure. You can observe quite a clear carbon-hydrogen stretch for the sp carbon, the hydrogen attached to a carbon involved in the triple bond, and that is absent in the spectrum at the bottom because these carbons do not have any hydrogen attached to them, therefore they're not going to show a band. Another interesting thing is that the carbon-carbon triple bond stretch, which appears very clearly in the spectrum at the top, is not visible in the spectrum at the bottom. And that is because, remember, for a mode to be visible in the infrared spectrum, it needs to change the dipole moment. And the symmetric stretching of that carbon-carbon triple bond would make a difference to the polarity of this bond, because you have a hydrogen on one side and a row of carbons in the other, but it will not make a difference in the dipole moment for this one, because the carbon triple bond is in the middle. So because it doesn't make a change, it doesn't change the dipole moment of the molecule, it's not visible in the infrared spectrum. So in this case, the CH stretch for the sp carbon-hydrogen bond is not visible because there aren't any, and in this case is not visible in the infrared spectrum because that stretching mode will not change the polarity, the dipole moment, of the molecule.